Hello, my name is Owen Haynes, and today I'll be presenting Physics 2212's Lab 6, Magnetic Braking with Faraday. So the purpose of this lab was to observe and evaluate how a magnet falls slower when dropped through an electrically conductive tube. First, we performed the experiment in real world and observed what happened, and then we modeled this interaction in GlowScript. And our results were that we found that the average falling time in the real world was 1.36 seconds, and the model's predicted falling time was 1.065 seconds. So the fundamental principles used in this lab: first, we have the Biot-Savart law that calculates the magnetic field exerted by a magnetic dipole moment at any point in space. We have Faraday's law, which relates the EMF to the change in flux. We have Ohm's law, which is V equals IR. We have Lenz's law, which relates the current and the length that it's traveling to cross the magnetic field to the force exerted on whatever you're analyzing. And we also have Newton's laws, which the second law, F equals ma, and then the third law, every force has an equal and opposite reaction force. So on the right here, you can see our experiment. We just have this tube wrapped in aluminum foil. We drop the magnet through, and we measure how long it takes to go all the way through. The system was the bar magnet in the tube, and the surroundings was everything else. On the left here, you can see the physical properties of the magnet and the tube. So here are our trial and our results, and the average time was 1.36 seconds. Next, after completing the experiment in the real world, we modeled this interaction using GlowScript. So first, in this slide of our code, we are establishing our physical constants for the tube, the magnet, and then just the universal constants. Next, we are establishing a function that calculates the magnetic field exerted from the magnet using the dipole B function. And then we're also establishing a function that calculates the flux going through a singular cross-sectional ring of the tube from the magnetic field by the magnet. Next, we're using Ohm's law to calculate the current flowing through one of those rings using the flux that we calculated in the previous slide. And then we're using that current to use Lenz's law to calculate the force that is being exerted on one ring by the magnet. And then we are summing up all the forces of all those individual rings, and then using Newton's third law, we know that the ring exerts an equal and opposite force on the magnet, meaning the force the magnet exerts on the ring equals the force the ring exerts on the magnet. So then we can sum up all the forces that are acting on the magnet, which are gravity, and then also the magnetic field to get the total force that's being exerted on the magnet. Finally, using Newton's second law, F equals ma, we can extrapolate from the acceleration, first the velocity, and then the position of the magnet, and iterate over time to find the position and the velocity of the magnet as it falls to the tube. So then here are the results. On the right here, we have a graph of velocity versus time. You can see that I've labeled as the magnet is entering and exiting, the force of gravity overcomes the force of the magnetic field, which causes it to accelerate. This is because there is less tube on the top when it's entering or less tube on the bottom when it's exiting to actually experience a flux and then create a magnetic field. So there's just less magnetic force. And then in the middle, there is material on the top and the bottom to exert a magnetic field, and the force of gravity and the force of the magnetic field equal each other, so velocity is constant during that time. There are a lot of assumptions made in this model. Only forces are from the magnetic field and gravity, and we're assuming that the dipole moment is always aligned with the axis of the tube, when in reality it could be tumbling a little bit and it's not always perfectly parallel to the axis of the tube. So the source of the error in this model, because our time that we got from this model is 1.065 seconds, which does not match the time in the real world. First of all, inaccurate magnet timing when we perform the experiment in the real world. Like I said earlier, the magnet could be tumbling and colliding with the sides of the tube, so friction between the magnet and the walls of the tube, and then also inaccuracies from those assumptions. All right, which color corresponds to clockwise current as viewed from above, and which counterclockwise? How can you know? So in the model, we were assuming that the magnetic dipole moment is pointing up. A current is induced to resist the change in flux. So because of this, red indicates clockwise and blue indicates counterclockwise. What happens to the dynamics of the system when you flip the magnet around? So the motion of the magnet wouldn't change, but the currents would be flipped because the magnetic field would be traveling in the opposite direction. How does the total time of the tube of your real-world system compare to that of your computational system? How may the computational system be made more accurate? I discussed that in the previous slides due to the assumptions and the errors in the experiment. And then what does the shape of the velocity versus time plot tell you about the forces acting in the bar magnet? Once again, gravity overcomes the force of the magnetic field when it's entering and exiting the tube, and then they're equal in the middle of the tube, causing the magnet to have constant velocity. And then finally, What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So by Ohm's law, decreasing the resistivity, which would decrease the resistance, would increase the current flowing through the tube. By Lenz's law, increasing the current would increase the force exerted on the magnet, causing it to fall slower. And then what if holes or slots were cut into the tube? How would this affect the ring of currents in your model? So a cross-section of the tube that contains a slot would be analogous to an open circuit, meaning no current could flow through that section. This means no magnetic field would be induced, causing the magnet to fall faster. Thank you.